Welcome to another practice session. So today we are going to have concepts and examples. I'm not going to do a whole bunch of problems. Just get everything ready to do more problems in momentum. So it's a pretty simple thing. So this is the definition. So this is just a definition. And this is the law. Okay. And these are all vectors. So make sure you really know how to do vectors, etc. If you don't know, maybe you can pick it up through these videos. Okay. So just briefly, I have a box. It's moving. Say box is 2 kilogram and it moving at 3 meter per second in that direction. Then we say the momentum, oh, that's not a good color. Just let's say pick a white. Then momentum will be in the same direction as the velocity. This is the velocity direction. This is the speed, and the arrow represents the direction. So same direction and momentum, and its magnitude, which we denote by like this, and we write it without the symbol of arrow over it. This will be just mv. This one we write v. V is the vector, and this is the magnitude. Magnitude is always going to be positive, the way we write it. Okay. The direction is in the arrow, so it's in the direction is not positive or negative. It's just arrow. If the arrow points in the positive x direction, then it's positive. If the arrow points in negative x direction, then it's negative. Okay. So magnitude is never going to be negative. It's always going to be positive. Those are components that can be positive or negative. So over here, you have a 2 kilogram, 3 meter per second square, per second. Together they make it 6 kilogram meter everything per second. Now this does not have any name to it. Okay. Turns out Newton is kilogram meter per second square. So you can see this whole thing will be Newton times second is going to be kilogram meter per second. So you could call this Newton times second, okay? But people just leave it like that when talking momentum. All right, so that's the definition of momentum. Let's do a little bit of math with the momentum. This is the second law. So this whole thing is can be think about you're gonna have vector will have time dependence. So this will be time dependent. So what this is at an instant pt. So this is at instant t, mass at that instant, velocity at that instant. And this thinking that everything is instantaneous formula here is important. Okay. So in here you can see this is a function of time, so I can take a derivative. That's what ma comes from, and this is this. So ma is not the fundamental law. This is the fundamental law. So this is written at instant t. Okay, I'm gonna speed up a little bit. So let's see what we're gonna do over here with that. So so this has actually, if you wrote down in x, y, and z, then the vector p at instant t has three parts. There's a x part, and there's a y part, and there's a z part. Okay, so this equation is actually one for the x part at instant t, one for the y part, and one for the z part. So normally you use Cartesian to decompose. You don't have to use Cartesian. You could use if you're in two dimensions, say x and y, you don't have to do Cartesian. You can use a polar coordinate, theta r. So theta goes this way, theta goes this way, and r goes that way. So it's turning out to be either use white or yellow. These other colors are not, doesn't work out very nicely. Okay, so we have these three equations. So if you can see, I can if you do a little bit calculus, this can go on the other side, and so you have a dpx equals to fx at time t dt. So I can integrate to get an integral form of this. So if you integrate, say integrate from t equals to some initial time to t equals to some final time, and so the values of this at this time will be this limit here, px, let's call it pxi for the initial, and this calls px final for me. So it's very easy integral. So px final minus px initial on the left side is, on the right side is just ti to tf fxt dt. So this has same, this is same as that. So when you write this way, you say I'm writing differential form of second law. When you write like that, you say I'm writing integral form. Now, but this is, there's this guy and this guy. Oh, so there will be three of these, and one for the x and one for the y, one for the z. So you can put them together in a compact way. But this is the way you can do algebra, but the compact is to, so p vector final, don't need to put x there, minus p vector initial. This abstract integral go from ti to tf. You can't do this integral, you have to do that integral. This is do this, okay? So this will be a vector, this conceptual. So this is called, compact notation is called conceptual. So this integral is called conceptual integral because there's no function like that. These are the x components of functions. Okay, so there is a x. So this one has three parts. So there are names to this. So this part, and I did this choice, wrong choice of color. This part is change in momentum during the interval ti to tf, and this part is what may have caused that. So this is like a cause of that. Of the change in momentum. and has a name. It is called impulse vector, or simply impulse. So sometimes I like to use this, but that's not a common notation, because I will be using a moment of inertia. The symbol almost reserves. So we use this for the impulse vector. So you can write impulse vector is the right side, and left side is change momentum. So this is so-called cause, and this stuff is called so-called effect. So there's a fundamental relationship between cause and effect. F, and it's got, so Ti to Tf is a definite integral, so we can just say in this, so impulse during that time, so the impulse during Ti to Tf, so it carries the information what you did. So you can write down Pf minus Pi is J initial to final. So this is the integrated second law. This is Newton's second law. All right, so that's a conceptual thing. I hope you got that. Let's do a little exercise here. So let's do an exercise. So say I have a box. I'm not going to give a mass and anything. So this is a Ti. Well, let's give a mass. Let's call it 2 kilogram. And let's see, it's at this point is going at 3 meters per second. All right. And so I want to know what happens over here. This is Tf is still 2 kilogram. I want to know how fast it's going over there. Let's call it V sub f. And during this time, let's call this x direction. If you look at the force, so say at some instant t, between Ti and Tf, if you look at the force and plot it, so this is the Ti, just conveniently put it 0, and this is the Tf. When you plot it, maybe it looks like it halfway there. It straight went to a value f0, and it came down like this. So it's like a bat hit this thing. So this is force kept getting bigger and bigger, and then force getting smaller. For not pulling back, it just force magnitude dropping. So if you want to do diagram, so here is this bigger force. Right at the top, the force is that big. Over here, force is still pointed to the right, but it kind of, so this is like a F here, F here, F here, and over here, when just over here, force is no force, and over here just started out no force. Okay, so that's this picture. Just instant after that, force start to pick up. All right, so what is the impulse? Well, it will be Jx, because we're talking about x impulse. and it's going to be ti to tf, and I'm going to have fxt dt. Now you can do this integral by finding the curve that's like that and then curve like that and plugging in there, or you can see that this is going to be the area under this whole thing, and this is 0, so area above 0, so this is going to just be area, so this is positive, so this is just going to be f0, and the difference is tf minus ti times tf minus ti, so that's the base, and the height is f0 divide by 2. So if the force was all the way here, then the area will be bigger, twice as big. That's why it's like that. So that's the answer for impulse. Let's call it a 5 Newton, and let's call this 0, and this called say 10 seconds. All right. So let's put the numerical values. So this is half times 5, 10 minus 0. So this is 25. So what's the unit? This is Newton and this is second. So the Newton times second. So that's the same unit, right? So, but when you say J, we use Newton second. So this must be equal to change in. So Jx would be P final x minus P initial x must be this. So that's the law. So this we figured out. Initially it was, this part is Vx is 3 meter per second and m is 2 kilogram. So P initial x is 6 kilogram meter per second. This one is 2 kilogram times Vx. This is what we don't know. So we want to figure it out. So that's a 2 kilogram times Vx of V final x, and this is 6 kilogram meter per second, and that's 25 Newton second. Now see, all of them SI units, so these units, carrying these units is too much work. Okay, so as long as it's consistent, you just don't write these units in the equation. So this will give me 6, bring it over there, and so V final x is 25 minus 6 over 2 is 19 over 2 is 9.5 meter per second. Okay, so that's the answer. Because that's how you do impulse. Let's do another example of, so this is another example, but this example will be a little crazy. Okay, so let's see, if you start out like same, still 2 kilogram, still going 3 meter per second. So let's say Ti equal to 0 at this initial instance, and you put a force, increasing force, but at this point you suddenly no force. You switch the direction. You say, I'm gonna start to push back way, and then I'm gonna over here, this is time axis, this is the x going on, but time here is t1, t0, let's call this t1, this time is t1, so this is time axis in a way. So over here I'm going to, and and here is T2 equals to T final. So let's see, you pushed for 3 seconds, and you pushed back for 2 seconds, and you're over here. Maybe you pushed back, let's see, maybe let's give them 5-second push. So I'm going to plot this to just give you a sense of what it might look like. Fx. So these are all positive, so it's going to be above it is 0, and then there will be up to T1, 1, 2, this is T, 3, 4, let's see, it went 5 Newton. So it increased and then suddenly stopped, and maybe it minus 3 Newton, but it acted over this much time. Okay, so it's pushing back over this much time. So that's what it looks like. So what's the impulse? Well, it will be this area plus this area. Now this is negative area, so this area will be negative area because it's below the line 0, and this area will be positive area. So Jx will be over here, it's going to be 5 times 3 over 2, so this is the case, plus this guy will be negative 3 times the amount of time it took is, this is 5 seconds, it worked, that's base 5 over 2, and you can see that this actually, then let's give it more numbers. Let's call this give it 8 seconds. How about that? So this is 3 plus 8 is, it went up to 11 seconds. So this is 11. So 3, so let's give it 8. So it's a little bit more complicated example. Okay, so you can already see that 5 of that will kill this part, and so you'll be left with minus 9 over 2, so minus 4.5 meter. It's going to be Newton times second. So now the impulse is this, and so we do the same thing to figure out what the Vx will be. It could be this way or it could be that way, so we don't know till we solve it. So I have a P final x minus P initial x should be equal to Jx. All right, so P final x is what? P final x is mv final x minus mv initial x equal to J initial final x. We're not writing that. Too much writing, right? Just writing Jx. So this one will be 2v final x minus 2 times 3 is equal to minus 4.5. So 6. So this brings 6 on the other side is 2vfx equals to Yeah, okay, so it is 6 minus 4.5 is 1.5. So v final x, now it's really slowed down. 1.5 over 2, 0.75 meter over second. So it's slowed down. The question is, could this be even reversed? What if we did this? Let's take a different color. Okay, so suppose suppose this went on, negative impulse went on for maybe this whole thing was 20 seconds. Okay, so what will happen? So positive part remain the same, this will get bigger. So in that case, Jx will be 5 times 3 over 2 minus 3 times 20 over 2. So I didn't increase the force acting, right? Just acted for a long period of time. So this is 15 over 2 minus 60 over 2 is minus 45 over 2, 22 Newton second. Now if you work out here, 2v final x minus 6 again, minus 22.5. Now this will overwhelm that guy. So 2v equals minus 20.5 plus 6. So minus 16.5. So v final x is equal to minus 8.25. I hope I didn't make some calculation. My intent is to get this negative. So it's negative. So I'm over here t final now, and v final x is minus 8.25 meter per second, and positive x-axis point that way. So it tells you the velocity is pointed that way and has magnitude of 8.25 meter per second. Okay, so that's the impulse and change in momentum works out. I think that I'll check if this is enough, and we are going to next talk about some basic ideas about collision. Okay.